Dear students, in the present class, we will discuss methods of estimation. As I told you in the last class, classical statistical inference has two branches: estimation and hypothesis testing. Estimation itself is divided into two. One is point estimation. The other one is interval estimation. Interval estimation. As we have discussed, Euler's estimators are point estimators, in the sense that in a given sample, we will obtain only one value for beta 1 hat and beta 2 hat. The concept of interval estimation has not been introduced so far. But when we consider hypothesis testing, there are two approaches to hypothesis testing. One is the confidence interval approach, and the other one is the test of significance approach. Confidence interval approach is based on interval estimation, and test of significance approach is based on point estimation and its sampling distribution. So my discussion of this topic is very general, not restricted to regression analysis or econometrics. My analysis is applicable in all the cases. So let us see what is the difference between these two, point estimation and interval estimation. Now, we often know that a random variable x follows a certain distribution. Say random variable x, height of the population, follows a certain distribution, such as the random variable x is normally distributed with the parameters mu and sigma square. But we do not know its parameters. We know that the random variable height is normally distributed, but the parameters are unknown. But remember this, in statistics, we are not much concerned with the entire distribution. Our interest is the parameters of the distribution. For normal distribution, the parameters are mu and sigma square. Our interest may be to make inference about the average height of the population of a particular community or a particular place, whatever it is. So, the nature of the distribution is known. Parameters is unknown. So, to estimate these parameters, unknown parameters, we assume that the random variable is normally distributed or follow a certain distribution, and we have a random sample of size n, a random sample of size n from this known population. That is, for example, if height is the population, we take say 50 samples from this non-population, and we use this sample to estimate the unknown parameters. In the case of point estimation, what we do is we assume that the random variable x follows a certain PDF distribution with the fx theta. Theta is the parameter of the distribution. Theta, my discussion is general. Theta is the parameter. Theta may be mu, theta may be OLS estimators or correlation coefficients, whatever. We assume that the PDF is normal. X is a random variable with a normal PDF. But the parameter theta is unknown. So we draw a random sample of size n from this non-PDF and develop a function of these sample values. We draw a random sample of size n from this non-population and formulate a function, say theta hat is a function of x1, x2, etc., xn. Theta hat is a function of the sample values x1, x2, etc., xn. Now this theta hat, as I told you, is known as the estimator or the sample statistic. Sample statistic or the estimator, a rule or formula which tells us how to estimate a population parameter. And we know that depending on how we develop this function, we have arithmetic mean and many other sample statistics. So in the case of point estimation, the procedure is we have a non-population with a PDF with an unknown parameter theta. We take a random sample of size n from this non-population and we develop a function of these sample values. And we call this function the estimator of the unknown parameter theta. It is a rule or formula which tells us how to estimate a population parameter. And a specific value obtained in a specific application is an estimate. Now this is the idea behind point estimation, something which we are familiar with, which we have extensively discussed in the previous classes. Now let us see what is this interval estimation. Interval estimation. Now we know that point estimation is a method of estimation, and point estimation will give only a single value for the parameter. Theta hat will give only a single value for the parameter theta. But we also know that the value of theta hat vary from sample to sample due to sampling fluctuations. And we do not know which theta hat represents the unknown parameter theta. Remember this, theta is the parameter, is a constant. For the population there is only one theta, but theta hat vary from sample to sample due to sampling fluctuations. Now, as the value of theta hat vary from sample to sample, due to sampling fluctuations. And as we are not sure about which theta hat truly represents the true theta, we can make statements involving probabilities. We can make statements involving probabilities where we use the idea of interval estimation. Now, in interval estimation, as against point estimation, instead of suggesting a single value for theta, say 150 for theta, we suggest a range for theta. We suggest a range in which the theta will lie. Instead of suggesting a single value for theta, in interval estimation, we suggest a range in which the parameter will lie. And the idea behind the notion of interval estimation is the concept of the sampling distribution of an estimator. An estimator is a random variable. The distribution of the estimator is known as the sampling distribution, and we use the concept of sampling distribution to construct what is known as interval estimation. In interval estimation, instead of suggesting a single value for the parameter, we suggest a range, say 140 to 160, and we say that the parameter will lie in such an interval. So the point is, instead of depending on the point estimation, we construct an interval around the point estimation, taking 2 or 3 standard errors in either side, such that this interval has, say, 95% probability of including the parameter. This is the idea behind interval estimation. Let me repeat. Instead of depending on point estimation, we construct an interval around the point estimator, taking 2 or 3 standard errors on either side. Taking 2 or 3 standard errors on either side, and we say that the probability is 90%, 95%, 99%, etc., that the parameter will lie in this interval. This is the idea behind what is known as interval estimation. Interval estimation. So instead of suggesting a single value, we suggest a range for the parameter. As an example, if x is normal with the mu and sigma square, we know that x bar is also normal with the mu and sigma square by m. Then we can suggest a interval such as x bar plus or minus 1.96 sigma by root n. We suggest an interval taking 1.96 standard error of x bar on either side. That is, if this is x bar, this is x bar plus 1.96 sigma by root n. This is x bar minus 1.96 sigma by root n. That is the 95% probability. So what we say is, if x is normal, x bar is also normal, and we construct an interval like this and say that the probability is approximately 95% that the intervals like this intervals like this will include the true parameter, then this is what is known as interval estimation. So in the case of interval estimation, instead of suggesting a single value for the parameter, we suggest an interval by taking 2 or 3 standard errors of the estimator on either side of the estimator and say that the probability is 95% or 99% that the parameter will lie in this interval. And this is the idea behind what is known as interval estimation. This is the idea behind interval estimation. And remember this interval is a random interval because it depends on x bar and its standard error. And it varies from sample to sample. So this interval will vary from one sample to another sample. And when we say that the probability is 95% that the parameter will include in such an interval, it must be carefully understood. Parameter is a constant and you cannot attach probabilities to constants. So what we say is, if we construct intervals like this in a repeated number of times, intervals like this will include the true parameter 95 out of 100 times. That is the meaning of the statement. Parameter will lie in this interval 95 out of 100 times. That is, suppose this is the position of mu. You construct an interval, mu is in the interval. Another one, mu is in the interval. Another one, mu is not in this. So if you construct 100 such intervals, parameter will be in the interval 95 out of 100 times. So construct the intervals in a repeated number of times and we can make probability statements about such intervals using the concept of repeated samples. In a given sample, parameter will be in this interval or outside the interval, we do not know. But if we construct such intervals in a repeated number of times, parameter will lie in such intervals 95 out of 100 times. More formally, let us give a more formal interpretation. So more formally, we want to find out how close is theta hat to theta. For that, we find out two numbers. We find out two positive numbers, delta and alpha. Delta and alpha, such that the interval theta hat minus delta, theta hat plus delta is equal to 1 minus alpha. The probability that the interval theta hat minus delta, theta hat plus delta contain the true theta is 1 minus alpha. 1 minus alpha. Symbolically, the probability that theta hat minus delta less than or equal to theta less than or equal to theta hat plus delta is equal to 1 minus alpha. So formally, we want to find out two positive numbers delta and alpha such that the probability that theta lie in these two intervals is equal to 1 minus alpha. Can also be written as probability that theta is less than or equal to theta hat 1, greater than or equal to theta hat 2 is equal to 1 minus alpha, where theta hat 1 is theta hat minus delta, theta hat 2 is theta hat plus delta. We can write it in any way. Now, this interval, that is theta hat 1 to theta hat 2, is known as the confidence interval of size 1 minus alpha. Confidence interval of size 1 minus alpha for theta. This interval is known as confidence interval, and 1 minus alpha is known as confidence coefficient. Confidence coefficient, and alpha is known as the level of significance, also known as the probability of committing type 1 error. The probability of committing type 1 error. 1 minus alpha is known as the confidence interval of size 1 minus alpha. 1 minus alpha is known as, the interval is known as confidence interval. 1 minus alpha is known as confidence coefficient. Alpha is known as level of significance or the probability of type 1 error. These concepts will be discussed later when we study hypothesis testing in detail. So even if you have doubts about these concepts, just ignore that. We will consider this in detail later. And theta hat plus delta is the upper confidence limit. This is the lower confidence limit. And for example, if we generally express 1 minus alpha into percentage terms, so 1 minus alpha into 100%. So if alpha is 0.95, this is equal to 0.95 over 95%. If alpha is 5%, for example, the probability is that this interval will include the true parameter is 95.95 or 95%. Now, remember this, the interpretation of confidence interval very carefully. The interpretation is, if we construct intervals like this, in a repeated number of times, the parameter will lie in such intervals 95 out of 100 times. We cannot say that the probability is 95% that the parameter will be in this interval, because parameter is a constant. We cannot attach a probability to parameters. So what we say is, if we construct intervals like this 100 times, then if alpha is set as 5%, 95 out of 100 times parameter will lie in this interval, and 5 times parameter will be outside this interval. So that is a point which must be kept in mind. Also, this interval is a random interval. It is a random interval in the sense that the value of the interval varies from sample to sample. As I told you, the interval will vary from sample to sample. We assume that each time we construct intervals like this, and remember this, for constructing this interval, we use the standard error of estimators. Let me consider an example. Suppose that the height of the population is normal with the mu inches. Sigma is equal to 2.5. Mu unknown, sigma 2.5. Suppose that n is equal to 100 is taken and x bar is 67. Now, let us see how we construct a 95% confidence interval for mu. Now, x bar minus 1.96 sigma by root n less than or equal to mu less than or equal to x bar plus 1.96 sigma by root n is the 95% confidence interval. Now, x bar is 67 minus 1.96 sigma by root n, 2.5 by root 100 less than or equal to mu, 67 plus 1.96 sigma by root n, that is 2.5 by root 100. That will give you 66.51 less than or equal to mu less than or equal to 67.4. This is the 95% confidence interval for mu. Remember this, mu is unknown. A sample x bar 67 is taken, 67 is a point estimator. So using this point estimator and also taking 1.96 standard error of the estimator, 1.96 standard error of the estimator, we suggest a range for mu. We will say that the parameter will lie in intervals like this, 95 out of 100 times. Remember this is based on one sample. If I take another sample, the interval will be different. Interval will be different. But if you construct intervals like this in a repeated number of times, the parameter will lie in such intervals 95 out of 100 times. We use the concept that the probability is 95% that the parameter will lie in such intervals in the longer run sense. You construct the intervals in a repeated number of times, then the parameter will lie in such intervals 95 out of 100 times. And remember also this, to construct such intervals, we use the standard error of estimators. 1.96 standard errors, 2 standard errors, 3 standard errors, we can use any number. If it is 1.96, then it is 95%. The construction of the confidence interval will be discussed in detail at a later time. This is only an example. How we actually reach this confidence interval is a concern of the next class. So remember this. In the case of point estimation, we suggest only a single value for the estimate, for the parameter. In the case of interval estimation, we suggest a range within which the parameter will lie. This interval is a random interval. It varies from sample to sample. And our statements about interval estimation is based on probability. If we construct intervals like this in a repeated number of times, parameter will lie in such intervals 95 out of 100 times. This discussion is general. This is the confidence interval, and 1 minus alpha is confidence coefficient. Alpha is known as the level of significance. These issues will be discussed in detail when we consider the issue of hypothesis testing later. So this is the problem of estimation.